Ladies and gentlemen, welcome to the presentation of Principles, Technologies and Functionalities of Smart Factory 4.0. This is a presentation given from the Division of Virtual Product Creation at the Fraunhofer IPK in Berlin. Well, to the agenda. First of all, we want to give you a brief overview on how Industry 4.0 changes digital manufacturing. The second thing is that we introduce you to the concept of digital twins. Then my colleague Thomas Vorsatz will give you a demonstration of the smart factory we realized. And yeah, the last point is an outlook on the current activities of the ProSTEP iViP. One of the basic ideas of Industry 4.0 is to implement and to use the Internet of Things to connect the industry, especially manufacturing companies. What we want to go for is creating a surrounding network that gives assistance to the people, to the machines, the objects and the IT systems in an interconnected way. The approach itself comprises a horizontal integration along the value-creating network, a vertical integration of the production and its IT systems, and we want to reach a consistency across the engineering and operation. Also, to this approach belongs the idea of decentralization, of providing intelligences and functions where needed, and also the people in this system are playing a big role. Talking about Industry 4.0, especially the term of CyberPhysical Systems is very important. CyberPhysical Systems are resulting from two views. On the one hand side, it's cyberizing the physical for specifying the physical subsystems with computational abstractions and interfaces. In this term, we are talking about digital twins. And physicalizing the cyber for expressing abstractions and interfaces of software and network components as well to represent the physical systems dynamics in time. To reach that goal, we connected embedded systems with smart sensors and interconnected those systems to reach the goal of having the ability created to communicate bidirectional. So now let's have a more detailed look on the concept of digital twins. This slide shows our vision of the digital factory twin. On the left-hand side, this is where all the digital models are developed. We call this type. This phase reaches from the development phase up to the point of start of production. We are using the models and the information of the digital twin for the product development, for the production planning, logistics planning, plant and facility development, quality assurance, and the virtual validation as well. On the right-hand side, you see the physical factory. All the digital models are becoming reality and you have your physical factory set up. On this hand side, we can capture different data and information like changes due to commission, maintenance, reconfiguration. We are also having process parameters of the equipment, operating and machine data and quality information as well. The innovation of digital factory twin mainly lies in the idea of connecting those separated worlds. What we want to do, or what we want to reach, is to continuously update the digital world with data from the physical factory. With doing that, we are developing new capabilities of having simulation and digital validation of the physical equipment in the virtual world. So what are the goals and benefits of digital factory twins? With the factory twins, you actually can accelerate your planning cycles. You can improve product quality And you have the feature of reproducibility and the ability of benchmarking different equipments in different sites. You also have the capability doing ad hoc simulation for small batches or never planned customer-specific products. All in all, you gain holistic knowledge and a decision base for your Industry 4.0 planning and decision processes. To position ourselves, but also to enable a more easy development of digital twins, we created an 8-dimension model. This shows which challenges have to be solved within the development of digital twins. It comprises the dimension integration depth, connectivity, the update frequency, the intelligence within the system going to artificial intelligence. It's the dimension of simulation capabilities, digital model richness, and of course the human interaction with the whole system and the whole product lifecycle. So let's get hands-on, from the abstract concept of digital twins to the reality. Within the last ProSTEP iViP symposium, we demonstrated our Smart Factory 4.0, which is a small cup coaster manufacturing cell that contains 3 models. Those are connected using a living digital twin that updates information from the physical cell to the virtual cell. We are using this Smart Factory to demonstrate some use cases. You will see the use case virtual commissioning and validation of HMI concepts, the synchronous behavior simulation, and the smart data and process visualization. Now let's go to my colleague Thomas Vorsatz, who's giving you the details.
The Demoiselle Smart Factory 4.0 is an exemplary production line that currently produces cup coasters as one-piece parts with customizable engraving. It consists of 3 modules, where the first one is displayed as physical module in this video, containing the raw piece storage and the CNC mill. Modules 2 and 3 of the cell are solely represented by their digital twins as displayed in the right screen above the module. The customer prepares the production process by defining the product in its geometric shape within design boundaries and selecting the material, both by using a web browser-based configurator tool. Furthermore, the customer identifies themselves and binds themselves to the product to be produced. The production process is then started by releasing the order within the same tool. The portal robot takes the desired raw piece, moves it to the weighing scale to determine the raw piece's initial mass before it is loaded into the CNC mill. After the milling, the new mass is determined again before the product is then transferred onto the driverless transportation system at the end of this module. In the future setup, the Caterpillar device then moves to the milled parts to the next module, where the final product is assembled. After finished assembly, the part is transferred, again on the driverless transportation device, to Module 3 directly into the quality check cell within Module 3. Depending on the results of the quality check, the product is either transferred back to Module 2 to undergo corrections of the assembling process, or, if passed, is transferred to the outlet storage by Module 3's portal robot. The customer may then identify himself to take the product being finally transferred via portal robot to the outlet to get hold of it. The physical modules and their digital twins currently exchange information and data using a central OPC server. This is one industry standard that is very suitable and easy to implement because a mechatronics concept designer as well as most industry PLCs provide the interface. It also allows for easy access of the data either on-site or from remote, using one of many applications for mobile phones or any Windows-based PC, up to using Microsoft Excel to push dedicated information cyclically onto the responsible's Office PC. One focus of the Smart Factory is to not only acquire data and present situations to the worker, manager and operator. It shall offer solutions rather than problem descriptions. The smart interpretation of sensor data, often described as extracting smart data from big data, is the crucial base for making plans and lines more effective and less prone to errors. The self-developed dashboard of Fraunhofer IPK, visible on the top left, is a user interface that provides and visualizes the mentioned. Process data, KPIs, and solution proposals are presented to the user. It is important to understand that the digital twin is not only a planning model like those currently used in plant or line planning. It should be understood as an enriched planning and by its new feature as a living model that coexists with the real plant. The big benefit therefore is that it survives the state of setting up the line and putting it onto duty. It drives and enriches the real physical plant over its time of use. The benefits are obvious. Further use of costly planning models that interact with the real plant to control, optimize, and feedback usage data into the production line itself and even earlier stages of line planning. The digital representation of future or already in use cells of a line serves even further demands. Without relevant additional effort, the model of, for example, Module 3 may be used to easily validate that the cell suits human needs in terms of ergonomic validation and human safety. You can train future shop floor workers on a purely virtual representation. Putting this representation into a virtual reality environment, you may get test personnel directly from the shop floor to interact with it without having bought a single bolt before. No physical prototyping needed here. This scenario also allows for making sure that your planned safety measures on the module to be developed are good enough to prevent the worker from hurting himself and therefore causing production standstill and further costs. You may invoke error situations on a pure virtual base and evaluate how human tries to cope with them. What type of safety measures does he or she try to override, such as doors, sensors, locks, light barriers? Make the cell safe to be used by humans and train the human to work safely with the cell. Virtual commissioning is of course one of the basic demands in today's plant planning processes. The current production line can be extended and reconfigured by using the digital twin only. Besides testing best arrangements without stopping production, the PLC programmers can implement and test fully against the virtual representation for a later seamless and non-disruptive reconfiguration or extension of the existing line. Furthermore, the demonstrator will serve human by ad hoc creation of individual assembly instructions for each customized product and even depending on the worker's technical and cultural background as well as possible handicaps. Another potential of Industry 4.0 is the adaptivity to unplanned situations. Such can be that for handling a product processed through a new set of grippers due to a very individual outside shape may be needed. The line can be extended by an additive manufacturing device for rapid tooling, such as a 3D printer, to generate a set of individual grippers. We call it tooling on demand. Finally, the latter and other situations require interconnected production capabilities. That could start from tightly integrated supply chains with delivery in time, up to the distribution of orders to different plant sites depending on machine availability and quality requirements. Those are just one of many applications and use cases the digital twin concept applies to. Now I'm giving back to Thomas.
Thank you, Thomas. And now back to the overview. Let's give an outlook on the current activities of the ProSTEP iViP. Realizing the vision of digital twins and Industry 4.0 is a very complicated topic. I think this became obvious within the last minutes. We are looking for partners from industry and the research sector to get into a dialogue about standards and technologies that are making Industry 4.0 and the digital twin real, to make it applicable to the industry. So we ask you to join the ProSTEP iViP Association, which is a strong community since 1993. Together with our partners, we are working on topics of model-based system engineering, PLM integration, and of course, digital twins. I thank you for your attention and feel free to contact us every time you want.